So this is a diagram showing you actually what's involved. Here you have the patient with a nose clip holding their cheeks and breathing in and out, just normal, quiet, tidal breathing, breathing in and out of the portable tremor flow device. Now what happens is there's a vibrating mesh here, and that vibrating mesh then transmits sound waves down the bronchial tree. So you are superimposing the oscillation from the tremor flow onto the patient's normal, quiet, tidal breathing. And it's that measured waveform which then generates what we call the respiratory impedance, which is a relationship of pressure to flow, which I'll show you later, the graph that you get out. And the respiratory impedance has two components. It has a component which is what we call in phase, which is resistance, which is exactly what it says on the tin. It's the resistance to airflow. And another phase, which is the outer phase, or if you like, the mirror image, which is the compliance or capacitance of the lung, which tells you about the elastic recoil of the lung. Now, when you're using this device, when you're using the tremor flow device, this is what it looks like. You can see it's very portable. You can move it from room to room. It's hooked up to any laptop. It's very easy to maintain. It's very easy to calibrate. You don't need one of these huge, 3-liter precision syringes. That's all you need to calibrate it. It's very user-friendly for the patient and for the clinician. And crucially, the data is very easy to export from the laptop. And that's why we've adopted this machine. We looked at all of the airway oscilometry machines, and in the end, we plumbed for this one. So this is what it looks like. This is what you get out. Now, do you remember I said it's a relationship of pressure, which can be centimeters of water or kilopascals, to flow in liters per second. Okay, so that's why centimeters per liter per second, pressure flow relationship. That's the impedance. And the impedance, as I've said, has two components. R stands for resistance and X stands for reactance. I prefer to call it compliance because I think that's more descriptive. And then the pressure flow relationship, the impedance, is then plotted against the frequency. So let's start with the solid line here, okay? This is the resistance line. And you can see when you plot the resistance line against frequency, there is considerable variation depending on the frequency. So at low frequencies, say at, at low frequencies at 5 Hertz, you can see the resistance is proportionally much higher than the resistance at a higher frequency at 20 Hertz. And that's because lower frequencies travel further and deeper into the lung, and higher frequencies travel a much shorter distance. It's a bit like the sort of the radio wave idea of, of long wave and short wave, that kind of thing. So what we have here is the resistance at 5 Hertz tells you about the resistance in the entire lung throughout all of the airways, from the trachea all the way to generation 23, whereas the resistance at 20 Hertz, or R20 to abbreviate it, tells you about the resistance in the central airways down to generation 8. So if you subtract total air resistance R5 minus central air resistance R20, you get the R5 minus R20. Total minus central is the peripheral airway resistance. So keep that in mind. The R5, R20 is something you're going to see through the rest of the talk, which is total minus central resistance, peripheral airway resistance. Now, if we then go to look at the interrupted line here, this is, if you like, the negative ping or the reflected capacitance wave which comes back. So this is the sort of the ping that comes back due to the elastic recoil of the lung. And this is called the reactance, denoted by X. As I said, I prefer to use the term compliance or capacitance because I think it's more descriptive and easier to appreciate than reactance. So this is telling you about the elastic compliance of the lung. This is the reflective wave. Now there are 3 measures here that you're going to see throughout the rest of the tour, which I'm going to describe to you. First is the reactance or compliance at a low frequency of 5 Hertz. So this tells you about the elasticity or capacitance of the lung in the small airways. Then if you take the line up to where it crosses the 0, this is what's called the resonant frequency. And this is the point at which capacitance and inertiance cancel each other out. So this is the line here. So that's the resonant frequency, which you'll see as well. The area under this curve from 5 Hertz to where it crosses the 0 line is called the area under the reactance curve. And so that's denoted as AX. So we'll just go over that again. Resistance at 5 Hertz, resistance at 20 Hertz, the difference, which is peripheral air resistance, small airway reactance, area under the reactance curve, and the resonant frequency. That's it. There's nothing more complicated than that.